let's picture the absolute worst, most unforgiving environment on Earth for structural metals. We're talking constant, driving salt spray, 100% humidity, relentless UV radiation, and mechanical stresses that just never quit. Yeah, welcome to the marine environment. I'm your host, and look, as a veteran structural engineer, I've spent years doing forensic analysis on why heavy-duty installations, the ones that look absolutely flawless on paper, actually end up failing miserably in the field. So today, in this explainer, we're tearing down the assumptions about marine cable tray systems. We're going to dig into the raw data, look at how these materials actually behave, and figure out why field failures happen even after someone just dropped millions of dollars on premium materials. Okay, let's dive into this with a quote I use all the time. A corrosion-resistant side rail doesn't compensate for the wrong fastener set. Honestly, you can go out and buy the most expensive, highly rated marine-grade materials on the planet, but if you neglect the system-level engineering, you're basically just buying a really expensive disaster. A cable tray isn't just a chunk of metal, it's a whole interconnected system, right? Rails, rungs, splice plates, hardware, and if literally one localized piece of that system is compromised, the integrity of the entire installation just drops to zero. Here's our roadmap for today's forensic investigation. First, marine corrosion engineering myths. Second, material salt exposure behavior. Third, 4 field failure cases. And fourth, standards and fixing details. Let's jump right into Section 1, Marine Corrosion Engineering Myths. We really need to clear the air here. There are some incredibly common and frankly dangerous misconceptions floating around out there, especially among junior engineers and marine contractors, about what it actually takes to survive decades of salt exposure. And the biggest myth? The idea that simply specifying stainless steel solves everything. You see this all the time. A contractor specs 316L stainless, slaps it on the drawing, dusts off their hands, and assumes the job is bulletproof. No way. The reality is radically different. In a marine environment, failures almost never happen in the middle of a beautiful, pristine, straight section of tray. A premium tray is utterly useless if the joints, the cut edges, and the fasteners are ignored. Corrosive marine environments don't attack your strongest points. They aggressively, relentlessly hunt down the weakest micro points in your installation. Which brings us perfectly to Section 2, Material Salt Exposure Behavior. Before we can accurately diagnose the failures, we have to evaluate our materials in the harsh reality of salt exposure. Let's walk through this material matrix. First up, galvanized steel. Its behavior in salt is sacrificial, meaning the zinc coating literally gives its life to protect the steel underneath. So its first failure point, exactly wherever that zinc gets depleted or scratched. Next, we've got 304 and 316L stainless steel. These guys rely on a passive chromium oxide layer. They are incredibly tough, sure, but their first failure point happens at oxygen-deprived crevices, where that protective layer simply can't regenerate. Then there's aluminum. It forms its own oxide shield, but it's highly susceptible to failing right at the contact points with other metals. And finally, FRP or GRP, fiberglass reinforced plastics. They don't rust. That's great. But their behavior in salt and intense sun means their first failure points are usually UV degradation or mechanical fracturing under heavy loads. The big takeaway here? Every single material has an inherent weakness. And that inherent weakness brings us to a super critical concept, galvanic corrosion. This happens when dissimilar metals are coupled together in a corrosive electrolyte, like salt water. Think about the sheer irony of this for a second. A well-meaning contractor spends a massive portion of their budget on a premium 316L stainless steel tray. But then, to save a few pennies, or honestly just out of carelessness, they install it using cheap carbon steel bolts. Well, the salt water hits it, galvanic corrosion kicks in, and those carbon steel bolts act as a sacrificial anode. They dissolve with terrifying speed, dropping your beautiful premium tray straight into the ocean. This exact dynamic is why the physical shape of the tray matters just as much as the material itself. In marine setups, the ladder tray is the absolute default. Why? Because it has minimal surface area for salt to cling to. It allows maximum airflow to dry out moisture, and it practically prevents water pooling. You should really only use perforated or solid bottom trays when it is strictly justified. Like say, if you absolutely need to protect cables from falling debris or direct physical impact. Because otherwise, a solid tray is literally just a shelf waiting to collect salt water. All right, let's look at the evidence in Section 3, 4 field failure cases. Let's step onto the scene of the crime and do a quick postmortem. If you are ever auditing a failed marine cable tray system, you're almost always hunting for one of these 4 culprits: joints, cut edges, fasteners, and water traps. These are your critical weak points. Like we said earlier, straight runs of metal are usually totally fine. It's the intersections, the modifications, and the connection points where the destructive power of marine corrosion gets its start. Let's look at our first 2 cases together. joints, and cut edges. When a cable tray leaves the factory, it's fully sealed, treated, passivated. It's perfect. But that perfect factory-made rail becomes an immediate liability the very second it gets modified on site. A tech makes a field cut to fit a corner, and suddenly bam, raw, untreated metal is exposed to the salty air. If those cut edges and joints aren't immediately and properly treated with cold galvanizing compounds or the right sealants on site, corrosion is going to start eating into that metal within days. Not years, days. Next up is case 3, fasteners, and specifically a highly destructive phenomenon called intergranular corrosion. This is a localized attack right along the microscopic grain boundaries of the metal. It frequently happens when the wrong hardware grade is specified. So you might have this high-grade tray, but if the fasteners undergo intergranular corrosion, they literally rot from the inside out, while looking completely fine on the surface. Then suddenly, under the weight of heavy marine cables, the fastener just snaps. It's a guaranteed, localized system collapse triggered by a component the size of your thumb. Our fourth case involves water traps. These are areas where standing salt water simply accumulates and has absolutely nowhere to go. I always have a bit of dry structural engineer humor when I see this in the field. It's like, hey, congratulations to the contractor on buying the absolute best FRP fiberglass tray on the market. It's just too bad you turned it into a permanent saltwater bathtub by forgetting to drill drainage holes. Standing salt water doesn't just corrode, it accelerates localized corrosion and material degradation exponentially. Let's figure out how to prevent this in Section 4, Standards and Fixing Details. Diagnosing the failures is really only half the job. The other half is actually applying the strict engineering laws required to survive these marine environments from day one. Professional manufacturers who build systems for data centers, rail transit, and heavy industrial plants rely on strict international and domestic standards to ensure survival. Take a manufacturer like Xinma, for example. Their manufacturing and engineering solutions strictly comply with IEC 61537, NEMA VE1, BSEN 5085, and GB 31251. Now, those aren't just random alphanumeric codes to memorize. Those are the rigorous testing thresholds for mechanical strength, electrical continuity, and corrosion resistance. If your materials aren't compliant with those standards, honestly, they have no business being anywhere near an ocean. So here is the absolutely crucial point. Merely buying standard compliant material is not the finish line. You must follow these mandatory fixing details. 1. Support spacing has to be calculated for wind and cable load. 2. Your fastener grade must match or exceed the tray material, period. 3. Movement allowance is required for thermal expansion. Metal expands in the blazing sun, and if it's bolted too tight, it's going to warp and snap. And 4, hardware compatibility must be verified to prevent that galvanic corrosion we talked about earlier. Adhering strictly to these 4 fixing requirements is the absolute only way to prevent the field failures we just analyzed. We've covered the myths, the science of salt exposure, the devastating field failures, and the strict standards required for survival. So I want to leave you with a provocative reality check, a real mindset shift that every engineer and contractor needs to make before signing off on a marine installation. Ask yourself this. Your tray material is rated for 20 years, but are your fixing details rated for even 1? System-level engineering is literally the only thing standing between a successful installation and a catastrophic failure. Thanks for joining me on this explainer. Until next time, keep analyzing and build it right.